Okay, hi, hello everyone. Welcome to section. Welcome in. The QR code for attendance is up on the screen now if you want to go ahead and scan it. I forgot what today's fun question is, or like the bonus question. Does anyone remember, or did anyone see it yet? She said no. She said we've been sitting here for 10 minutes. We said we're not going to scan this. But it has the normal things. And what's the last question? Like I normally try to do, like a. Yeah, what's a hot take? Tribute a hot take. My favorite response I got from the fun fact question is someone said that they have like a former pet rat named Becky, and I love that. That's great. Tell me about Becky. Yes. Okay. So 3 little reminders at the start. 1, I'm horrible with names, so we're still going to be using the format of "Hi, my name is blank. My question's blank" for when we call on you, raise hands, all the things. 2, I also like to give a little disclaimer at the top of the course of like, I can be a little sassy with my responses, and I know that this class can be stressful, and so sometimes sassy is not the right vibe for when you are stressful, and so if I misread a signal, know that that is me misreading a signal and not me trying to antagonize you, and I genuinely do not mean ill will. I just think that sassy is a little bit more entertaining than, well, yes, the lone pair then attacks the carbonyl, like. And then the third thing was if you requested printed materials and have not gotten one of these orange books from me that have the printed problem sets, come see me afterwards. I'm keeping track of like who has picked them up because we only have enough for the folks who ordered them right now. So cool. Today's plan for section, we're going to have 3 big topics and we're going to have 2 pretty hard pivots in between them. So we're going to start off talking about functional groups. Then we are going to go to MO theory with these 2 topics in the middle. And then lastly, we're going to do acidity, and acidity is here with the extra challenge problem. So we have 3 big tiers. Any logistical questions before we jump into functional groups? Cool. So functional groups are groups of atoms within a molecule that have distinct properties and react in a characteristic way. Basically, we need a way of we look at a molecule for the first time and we flag areas of that molecule that we know are going to react in characteristic ways. And functional groups gives them a name. So I literally think about it like tagging data or something. So this is going to be your kind of definitive chart for the functional groups you need to know. The problem set has some other ones that are a little bit more niche, like a thioether. We're not going to ask you about that on the test. And if we did ask you about it, I would give you a heads up. But these are the main ones, and I also tried to do some legwork to organize them to make them a little easier to memorize and think about. So I'm going to talk through these very briefly. First up, we have the hydrocarbons. So hydrocarbons, only carbons and hydrogens. And the most basic scenario that we have is an alkane. Alkanes, I wouldn't actually call a functional group because they're really the absence of a functional group. Alkanes are boring. Here we have Rs, and our R is a stand-in for more hydrocarbon chain or more alkyl groups. So like this R could be like an ethyl, or it could be like an isopropyl, or it could be like a long blum 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 blum, whatever. We don't care because it's not something that's affecting the reactivity there. So R is just our general shorthand abbreviation for something that's carbons, like probably an alkyl group. Then if we have a carbon-carbon double bond, we call that an alkene instead of an alkane. And on the double bond, we can have either R groups or H's. It doesn't matter. That's what this notation means. So we could have it like this be an H, this be an H, this be a carbon chain. Sure. And then if we have a triple bond, it's an alkyne. So the nice little pattern is as we move from single to double to triple bond, we go from alkanes to alkenes to alkynes. We're going in ABC order, which I think is a little helpful. Then, if we have a ring where there are double bonds on all of the atoms in the ring, we call it an arene ring. You might also have heard it called a aromatic ring, and you could also call it a phenyl group. Like all of those are fine, but for functional group name, I would go with arene. So that's the hydrocarbon family. The next family I typically call the oxygen mafia because it's like oxygen and all of like the relatives. So our simplest oxygen functional group is an alcohol, and the sulfur version of an alcohol is called a thiol. So it has that OL ending. We include thiol in with all the oxygen ones because she's in the same column of the periodic table. So we know sulfur is going to react similarly to oxygen. Now, an alcohol has a carbon on one side with our R group, and it has a hydrogen on the other side. But if we have carbons on both sides of the oxygen, then it becomes an ether. Okay, so ether. Then, if we connect the two carbons that are on either side of an ether, it makes a little triangle. She's called an epoxide. She's very reactive. She likes to pop off. She likes to explode, very specifically. So we have to watch out for Miss Epoxide. Then, what if we have two ethers attached to the same one carbon? Then that is called an acetal. So if you were to see something like this on a molecule and you circled this and said ether, we have to mark that wrong. It is an acetal. And the reason why ether is wrong there is because ethers react in a very specific way, and acetals react in a very specific way. So if you flagged this as an ether, it doesn't react that way. That's why it's got to be wrong. And so acetal is when we have two kind of like ether substituents here attached to the same carbon. And if we replace one of those OR groups with just an OH, then we call it a hemiacetal because it's halfway to an acetal. Cool. Then, if we have a nitrogen around, and it can either have hydrogens or carbons on it, we call it an amine. So an example of like a nitrogen, H2, blah, blah, blah. So this is a nitrogen that has three things attached to it. One is a carbon chain, two of them are hydrogens. Here's one where we have three carbon chains attached to it, and it's still an amine. Then, if we have a halogen on a molecule, we call it an alkyl halide. The last little family are the carbonyl compounds. So we'll start off with a CO double bond, which we call a carbonyl. Now a carbonyl is not a functional group label. If you write carbonyl on the functional group question, you will not get points because she is an umbrella term. Can we all say that the carbonyl is an umbrella term? The carbonyl is an umbrella term. Thank you. So let's talk about the specific ones that can actually earn you points. So the most basic carbonyls are ketones and aldehydes. So if we have carbons on both sides of the carbonyl, then it's a ketone. And then if we have a hydrogen on one of the sides, it becomes an aldehyde. The little mnemonic from biology is aldehydes always have to be on the end of a molecule. And so we say aldehydes can't hide. And then, I don't know, hide. There's like an H. Trying with the mnemonics. I'm not really sure. Then we can think about if we have a carbonyl plus another functional group next to it, it becomes this new name here. So if we have a carbonyl and we have an alcohol, it becomes a carboxylic acid. Now, why does this react like one thing instead of reacting like a carbonyl sometimes and an alcohol at other times? Why does this react as one group? Any ideas? Resonance. The answer 80% of the time in the class, resonance. So we have a lone pair here. We know by our neighbor rule, this is actually going to be an sp2 hybridized carbon, or oxygen here, because it appears to be sp3, has a lone pair, and is adjacent to a pi bond. So we have resonance that we could do over here. So that's why it reacts as one unit. So carboxylic acid. If we have a carbonyl with a little ether side chain, we call it ester. So like every time I'm at a coffee shop, I hear like latte available for Esther or whatever. I think, oh my gosh, Esther, I know how she reacts. I don't know. Then amide. If we have a carbonyl and an amine, it becomes an amide. And then a carbonyl with a chlorine, an acid chloride. The weird one that we put over here is a nitrile. So that's a CN triple bond. It's not going to be clear why we include that in the carbonyls right now. But later on, you'll learn that she does a lot of similar reactions to all of these over here. Lastly, I want to talk about compound functional groups, which you are not tested on. Like, you will not need to know this. But she does appear in lectures 3 and 5, which is why I want to give a little primer on it. So let's say we have a ketone right next to an alkene. We would actually consider this to be one functional group because they're connected via resonance. And so we would call that an enone. Okay. Then if we have an alkene and an alcohol, we would call it an enol. And it's because, yet again, she has resonance. So it functions as one group together. That's why we combine them. If, however, we had another carbon between them, then is there resonance between these two sections? No. Why do we know that there's no resonance? What type of orbitals do we need for resonance? P orbitals. And what's the hybridization of this? Yeah, we have 2 hydrogens here, so she's sp3. So these are completely disconnected. There can't be resonance between them. That's why this is a ketone plus an alkene, not an enone. Yeah. Yeah, it does. So you can do a resonance structure that looks like this, where you have O minus, and then double bond here, and then a plus here. Yeah. And what's your name again? Machia. Yeah. Yeah, sure. So what it would be is you would have double bond OH plus and a minus here.
Oh, on the carbon.
Yes, on the carbon. Cool. So in the survey, I said if you are a paper user to write out these molecules, and if you're a tablet user, then bring up these molecules. And I want you to just try to label as many as you can from this. And what you would do is you would just circle it. So I'll circle this and I'll write alkene. I'm going to give you like 3-ish minutes. Remind me your name. Remind me your name. Nari. Okay. What's your name? Maya. And your name? Ronnie. Work. Nari. Maya. Ronnie. Are you Colin? No. Cam. Okay. And wait. Are you Cameron? Okay. We have Cameron. We have a Nate and we have a Nathaniel too. So. What's your name in blue tank? One more time. Rima. Rima. Okay. You just told me your name. Evram. What? Sarah. Nari. First letter? Rami? No. Yeah. Ronnie. First letter? M. Maya. Right. And what's your name? Nahal. One more time? Nahal. Nahal. And on the end, Hannah. Right. Ooh. probably know that you have not done all of them, but check the ones that you have done and see if we got the same thing. And if you wrote down a different thing, ask me about it. Because I guarantee you're not the only person who wrote down the wrong thing for that. Oh, ignore her. Spoilers. She's coming next. Yeah.
So for the ether, right? It is, the idea is that it has the C on both sides
Mm-hmm.
as carbon, but this is not a carbon.
Wow, what is ME short for? It's short for methyl, which is our abbreviation for a CH3. So I actually put this here intentionally, not to like trip you up, but so you get used to seeing things in various forms. So ME is short for CH3. And that's on the little nomenclature handout from the last section. Yeah. So carbons on both sides. Yeah. Yeah.
But M in the middle, why? Because it has like a basic
Mhm.
natural ability because
The big thing that we have to check is she next to a carbonyl? So because she's next to a carbonyl, carbonyl plus amine is an amide. Yeah. And you're Hannah. Remind me your name again. Matya. Work. Again, it's going to take me a hot second, and I will be quizzing myself when y'all are like working on things. Okay. So I'm going to go ahead if there are no other questions. And I'm going to teach you one other thing that has not technically been covered in lecture, but it will be covered. And I think it makes sense to think about when you're thinking about functional group names. So I'm going to teach you about classification. So not all carbons have the same kind of reactivity. Like not all carbons are going to be considered equal in this case. So we look at a carbon and we ask ourselves, how many carbons is it also attached to? So this carbon is attached to one other carbon, so we would say it's a primary carbon, or we would write 1 with a little degree sign next to it. This carbon's attached to 2 carbons, so it's a secondary carbon. This carbon's attached to 3, so it's tertiary. This one, 1, 2, 3, 4, so it's quaternary. And then if it's not attached to any other carbons, we'd say it's a methyl carbon. So in, where's a good example? What type of carbon is this? Primary, secondary, or tertiary? Tertiary. Great. I'm going to ask you a hard one. What type of carbon is this? Primary. It's only attached to one other carbon. Great. What about... Actually, I'm just going to do that for now because we're going to do more practice. When we have an alcohol or an alkyl halide, we can then classify the alcohol or alkyl halide by the carbon it's attached to. So if an alcohol is attached to a primary carbon, we call it a primary alcohol. If an alcohol is attached to a tertiary carbon, we call it a tertiary alcohol, so on. Same for the alkyl halides here. So for this alcohol, is it primary, secondary, or tertiary? So this carbon is attached to how many other carbons? 2. So it's a secondary carbon, so this is a secondary alcohol. Okay. What about this alkyl halide? So this carbon here is attached to how many other carbons? 2. So it's what type of carbon? So it's what type of alkyl halide? There we go. Then we have one other mix-up of this, which is alcohols and alkyl halides, it defers to the classification of the carbon, but for amines, it's about how many carbons are attached to the nitrogen. So here, there is one carbon thing attached to the nitrogen, so we say it's a primary amine. Here there are 2 things attached to the nitrogen, so it's a secondary amine. Here there are 3, so it's a tertiary amine. So like if we look at this nitrogen right here, how many carbon things are attached to it? 2. So we would say this is a secondary amine. And then what about this one up here? Is it primary, secondary, or tertiary? Primary, because it only is attached to 1 carbon. And we do, for amines, how many carbons it's attached to. We're never going to test you on this, but we want you to have specific language to talk about molecules, because then you can move from a visual language into terminology that you can actually like study and memorize. And there are going to be some reactions that only happen with secondary alcohols and primary alcohols, but not tertiary alcohols. And like having the words to describe that I think is important. But you will see this in like lectures 3 and 5, I think. So, yeah.
So does it mean that like as we go down to you, let's scroll up a little, the carbon.
Mm-hmm.
As we go down, there's like less reactivity. Like is the methyl more reactive than the ordinary carbon?
It doesn't always work that way. It depends on the reaction, but it's going to be important to distinguish for later. Yes, so it's not directly linked to reactivity in like a broad way. Yeah, but in specific reactions. Cool. So why are we doing functional groups? Let's look at this list of 3 reactions here. And what functional groups do you see on the left molecule for all of these? Carboxylic acid, yeah. So we have carboxylic acid, carboxylic acid, carboxylic acid. Then what functional group do you see in the right molecule? Alcohols. And let's classify them. The top one's what type of alcohol? Primary. Middle one? And last one? Primary again. Okay, cool. And these are all alcohols. And then what functional groups do we have in the product? Latte. Ready for? Ester. Ester. So carbonyl right by an OR group is an ester. So I could generate a list of like 50 more of these, because let's look at what's changing in this reaction. What's changing are these R groups, which appear in our product, yes. Like here, these 2 wind up on the other ends. Here, this is over here, this is over here. But if I wanted to, I could write out like 50 more of these. And I could be like, okay, memorize all these reactions. You're going to have a test on that. But if you go about approaching it without functional groups, these are all separate reactions. Whereas if you learn it with a functional group lens, this is one reaction. And then you can do all the versions of it with no matter what the alkyl groups are. This reaction is a carboxylic acid and alcohol under acid makes an ester. And you're going to learn that reaction in lecture 5. So that's why we are doing all of this and why it's going to be important when we start learning reactions in lecture 3. So I would say come in over the weekend, go ahead, do your studying on this, and like know it cold by like Tuesday. Tuesday's lecture, come in, functional groups. Any questions on functional groups? Okay. Yeah?
Do you need to know how to name them? Like naming as in like
Like nomenclature, the long names? No. You're only going to be given like simple nomenclature examples. Yeah. Yeah. Some classes are real intense. They spend like a month on naming. That's not us. We don't really care. You're going to have like a very basic like 4-point naming question on the test, and it's going to be like hydrocarbons, maybe 1 alkene or like 1 bromine on it or something, but it's not going to be crazy. You'll see more examples in the problem set 1 and 2. Yeah. Now, I told you we have to do hard transitions to move to very different topics. So in the past, one thing that I've done to ease the transitions is I've gotten transition sound effects from sitcoms and shows from my childhood. So I'm going to play a transition sound, and then we're going to hard pivot into a new thing. So let's see if it actually plays. So molecular orbital theory. Let's see what's going on here. Molecular orbital theory takes us from atomic orbitals, Gen Chem land, into the reactions of whole molecules. So a few key ideas here. First key idea is our number of atomic orbitals for a molecule is going to be equal to our number of molecular orbitals. So if you want to figure out how many molecular orbitals are in a molecule, we can just calculate the atomic orbitals. So for this calculation, hydrogen only has 1 atomic orbital, an s orbital. And then assume all other atoms have 4 atomic orbitals, like an s and then 3 p's. So over here in C3H7O, what we would do is, well, we have 7 hydrogens, each have 1 orbital, atomic orbital, and then we have 3 carbons and 1 oxygen, so that's 4 atoms, and each of those are going to contribute 4 orbitals. So in total we have 7 plus 16, so 23 atomic orbitals. So how many molecular orbitals do we have? 23 molecular orbitals. Okay, so what about C6H6? Can you try it out on your own very quickly? So we have 6 times 1 for the hydrogens, and then we have 6 times 4 for the carbons. So that's going to be 30 atomic orbitals, 30 molecular orbitals. Does that feel okay? Cool. Second big idea. For every bonding molecular orbital that we have, we also have an anti-bonding molecular orbital. And I know everyone has had different levels of physics in the past before this, but I think one helpful idea from physics is the idea of wave interference. And so, if you haven't seen it before, it's not a big deal. But there's a way that you can combine waves that strengthens the wave, that increases the amplitude of it if they align in phase. So that is going to be like our bonding interaction, where we are combining 2 wave-like things. And remember, we talked about electrons as having particle-like and wave-like properties. When we combine them in phase, then we get a bigger or more stable bonding molecular orbital. But then, if we were to combine 2 waves out of phase, what we would have is destructive interference, which is going to cancel out. And this is our idea of the anti-bonding orbital. If we combine things out of phase, they're going to kind of cancel out. So, second big idea, for every bonding orbital, there's an anti-bonding orbital. Let's talk about how we actually draw these molecular orbitals. So you did some drawing of these in class. And for the equally shared ones, like carbon-carbon bonds, then it's nice, symmetric, even. And we see that the bonding interaction here is in phase, and then the anti-bonding interaction is out of phase, so it creates an extra node here. But I want to focus on drawing the orbitals that are not equally sharing the electrons. So, when we have a difference in electronegativities, in the bonding molecular orbital, we have larger lobes on the more electronegative atom. So, if normally it would be a loaf if it was shared evenly, then here, where it's not equal electronegativities, we're going to have a larger lobe on the oxygen. So that's kind of how the pi bond would look here between carbon and oxygen. But then, for anti-bonding orbitals, we have larger lobes on the less electronegative atom. So it's going to look like this, but we're going to make the larger lobes over here, and then smaller lobes over here. So let's say we wanted to have a donor attacking a carbonyl, and it's going to put electrons in the pi star CO. So it's going to put electrons in this anti-bonding orbital. Is it going to attack the carbon side, or is it going to attack the oxygen side? Like, is it going to go and attack here, or is it going to go and attack here? What do you think? Carbon. Why? It's the one with larger lobes. It's literally like the easier target for the nucleophile to go and attack. That's one reason. Can anyone think of another reason? It has to do with bond polarity. Yeah, so if we look at the unequal sharing of electrons, we know that this oxygen's going to be partial minus, this is going to be partial positive. And so if we're coming in with electrons, we're negatively charged. We can be a neutral molecule, but electrons are still negatively charged. We are going to go towards the thing that's partial positive, because if we try to attach the thing that's partial negative, we'd have kind of electronic repulsion of the partial negative and the negative. So, both for space reasons of the orbital is bigger for the antibonding orbital, And for like this electronic reasons of having more of a partial positive, the nucleophile is going to go and attack the carbon. Now, this carbon already has 4 bonds, right? So what do we have to do? We have to break a bond. If we're trying to go and attack it and make a new bond, we have to break a bond. So we're going to break this pi bond. And the reason that we broke the pi bond is because we put electrons in the antibonding orbital. So there's the statement, electrons and antibonds make the bond break. And I hate to use Pavlovian conditioning, but we are going to say this as a class 4 times because it's important and it's going to come back. So we're going to start off in a very like quiet tone. So electrons in, antibonds make the bond break. Okay, now you're like chatting, normal conversation volume. Electrons in, antibonds make the bond break. Now you're trying to get someone's attention from across the room. Electrons in, antibonds make the bonds break. Now you're trying to save a little old lady from being hit by a school bus in the crosswalk. Electrons in, antibonds make the bond break. Cool. So if you ever put electrons into an antibonding orbital, what has to happen? Got to break the bond. Exactly. And we are going to see that when we are doing mechanisms for actual reactions. Great. So let's talk a little bit about the relative energies of our MOs, and then we'll put this into practice. So I like to think about these different molecular orbitals as being in different kind of energy buckets here, where our lowest energy bucket are the sigma bonds, slightly higher are pi bonds, then we have our non-bonding orbitals and atomic orbitals, we have pi stars, and then we have sigma stars. So these buckets look symmetric, right? Like the lowest energy is sigma, the highest energy is sigma star. But within the buckets, the thing that wins is the low energy trifecta. So, like if we had a sigma CH, CC, and CO, CO would be the lowest because it has the most electronegativity of those 2 elements. Now, if I had a sigma NO, would I put it at position 1, 2, 3, or 4 here? Where does it fit in relatively? It's going to be at 1 because, let's compare it to CO. Nitrogen's more electronegative than carbon, and so it's going to be even more electronegativity, lowering the energy. So our sigma NO is going to be even lower. Yeah.
Hey, my name is Mancia.
Mancia.
So the thing is, we don't care about the more color the bond. We care about the more electronegativity is both atoms, right?
Yes. It's not about the difference in electronegativity, it's about the like sum of electronegativities. And there are actually different ways to calculate it, but like for ours, I think sum is the easiest way to think about it. Yeah. So if there was total symmetry in our MO diagram, we would expect, okay, if the sigma CO is our lowest energy sigma one, we would expect sigma star CO to be the highest. But that's not what we see. What we see is actually, it's like we copied and pasted this over here and put little stars by it. So within this bucket, the sigma star CO is still lower in energy than sigma star CC, sigma star CH. So the most common mistake I see on the MO question on exams is students do a completely symmetric diagram, and only the buckets are symmetric, not within the buckets. Does that kind of make sense? Okay. So let's try to put it together with a practice. So I have the last page of this is a practice handout where I've just put some of the practice problems. Normally I try to do problems from the problem set so that we can already be knocking them out, but I wanted to do a full MO diagram with y'all pretty quickly just to show you each of the steps in order and how to do it in a kind of regimented approach. So we are going to be doing it for formaldehyde, CH2O. Our first step is to draw a Lewis structure. So CH2O, and then I'll do the valence electrons and finish off the Lewis structure. So how many valence electrons does carbon have? 4. Oxygen? And then each of the hydrogens have 1, so that's 2. So we have 12 valence electrons. Right now we have 2, 4, 6 accounted for. So 8, 10, 12. But then this would have minus charges without a plus. So I need to make a double bond. Okay. And then let me check. 2, 4, 6, 8, 10, 12. I have all my electrons. I have my Lewis structure. Okay, step 2, get the number of atomic orbitals. So hydrogens. Each hydrogen contributes 1. And then we have a C and an O, so we have 2 atoms that are contributing 4 because we have the S and 3 Ps. So that's going to be a total of 10 atomic orbitals. So how many molecular orbitals do we have? 10, because they have to be equal. Okay, so now our next step is list out all of 10 of those molecular orbitals. And the reason why we write this out is to make sure we don't forget any. So my strategy is I start with all the ones that we know, like that we can see here, the bonding ones. So I know we have 2 sigma CHs, we have 1 sigma CO, and we have 1 pi CO. Okay, well, those are the ones I can see. Then we think about the ones we can't see. So if we have a bonding orbital, then what do we also have? Anti-bonding. So we have 2 sigma star CHs, we have 1 sigma star CO, and we have 1 pi star CO. And if I count these up, we're at 8. So I'm missing 2. What are the 2 I'm missing? The lone pairs. So the lone pairs, they're not doing any bonds, so we use the subscript N for non-bonding, and they're on the oxygen. So we have 2 non-bonding oxygen molecular orbitals. So that's all of 10 of them. We're ready to jump into the actual building of the diagram. So we need to first put them into their buckets, energy level wise, and then for anything in the same bucket, then we use our low energy trifecta. So our lowest bucket is the sigma. So in our sigma, which one's lower in energy, CH or CO? CO. So I put my 1 sigma CO, my 2 sigma CH. Okay, next bucket is pi, where we only have 1, so pi CO. Then's our non-bonding bucket. So we have the lone pairs on oxygen. Okay, then we have the pi star bucket, so pi star CO. And then we have the sigma star, where we have these 2. Now, which one's lower in energy, the sigma star CH or CO? CO yet again. And so, because I'm on the iPad, I'm just going to copy and paste and put a little star. Okay, last step is you populate your MO diagram with your valence electrons. So we have 12. We put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the MO diagram. You will have one page of your exam be an MO diagram that is this for probably like 6 of the points, and then another 6 points is predicting how the molecule reacts after building this, which we're going to practice in a minute. Yeah. Yeah, so for hydrogens, we assume that each hydrogen contributes 1 atomic orbital, just the s orbital. So we do 2 hydrogens times 1 orbital each. And then for carbon and oxygen, for anything that's not hydrogen, we assume it contributes 4 molecular orbitals. So we have 2 atoms that are not hydrogen, and they're each contributing 4. So then if we multiply those out in an atom, we get 10.
Oh, so anything besides hydrogen.
Yes. Mm-hmm. Yep, totally. So with that, I have just done this kind of guided example for you and a simple one. What I'd like you to do is I'd like you to go to page 29 of the skill builders and look at this molecule hydroxylamine, which they used to have hanging in the science center. There was like a big thing hanging from the ceiling, and I think that they've moved it because the construction. But I want you to do this exact process of getting the MO diagram. And so you can follow these steps: Lewis structure, valence electrons, atomic orbitals, molecular orbitals. And then we will check over it quickly. So, and this is on page 29. Nine?
Yeah.
Don't tell me. Don't tell me. No. Ronnie? Maya. Ephraim? Did I pronounce that right? Makia? What's her name? One more time. Nima. Perfect. Nima. Hal, Burke, Hal, Rachel, and the yellow cardigan. So you'll use the same low energy trifecta. So if you have lone pairs on oxygen versus nitrogen, then the lower energy is the more electronegative. Mhm. Matcha.
Fractionating structure,
Mhm.
one of the resin structure can actually break the optical state, right?
For our class, the resonance structures can't.
Perfect.
So if you are done or nearing done, you can check up here. Okay. So any questions on this process so far? Anything that you ran into that was kind of tricky? To be so honest, I think this process for simple molecule, it's not that it's like conceptually difficult, and it's much more that like you need to get fast at it. Like I would say this by exam time, you want to be able to do this in about 6 minutes. Maybe less. Maybe 5 minutes. Ooh. So yeah.
Where do you get the five the valence electrons?
Nitrogen has a valence of 5. Oxygen has 6, and then 3 from the hydrogens. Mm-hmm.
How do we multiply the 2 by the 4?
So we have 2 atoms that are not hydrogen. So each of those 2 atoms contribute 4 orbitals. Mm-hmm. Yeah.
And there's a vacant non-bonding orbital.
Mhm.
How do we write them for like 2 with the 5? Or the carbocation?
So carbocations, like if they are vacant, they're typically going to be higher in energy than occupied ones. So like lone pairs would be here, and then right above it you would have like 2p on a carbon or whatever, if there was a carbon. Yeah. Mhm. Cool. Okay, we are still in molecular orbital theory land, but let's now talk about the frontier molecular orbitals. So the frontier molecular orbitals are ones that are on the, quote, frontier of reactivity. They are your highest occupied molecular orbital and your lowest unoccupied molecular orbital. And so for your class, you need to get very good at spotting a HOMO or a LUMO. Why do we care about these? Because these are the orbitals that are most likely going to do the actual reactions. And also, like the process that we just did with an MO diagram, like, yeah, we can do it, but we don't want to have to do a full MO diagram every time we want to predict how a molecule is going to react, right? We want little shortcuts for ourselves. So what we're going to look for are donors and acceptors. So a shortcut for good donor orbitals, we want the donor to be high energy, right? So lone pairs are typically some of the highest energy donors that we've seen so far because they're in the non-bonding level. And our exception is not lone pairs on halides are not that good of donors. They're not good on fluorine because fluorine holds them too tightly because it's so electronegative. And then for chlorine and beyond, they're not great donors because they're so spread out that it's not concentrated enough to be a good nucleophile. Then alkenes are other good donors because right below the non-bonding level, we have the pi bond level. So it's going to be high energy. You also, in a double bond, have a lot of buildup of electrons in one spot between these two orbitals. Or between these two atoms, I should say. Then, acceptor orbitals, we have three common good acceptors. One are empty orbitals, so those are going to be the best because they are the lowest in energy of the unfilled. Then we have the pi star orbitals, with the exception of the pi star CC. The reason why pi star CCs aren't good acceptors is because it's too even. You want to have this uneven thing in order to make it a better acceptor. And then lastly, sigma star CX orbitals, where X is something like electronegative. So these are kind of general terms of donor and acceptor. And then HOMO and LUMO are going to be like specific molecular orbitals based on the MO diagram. But then let's talk about the molecule as a whole. So if a molecule acts as a donor in a reaction, we call it the nucleophile. And if it acts as the acceptor in a reaction, then we call it the electrophile. And then the way I like to think about it is a special type of interaction or a special type of reaction is an acid-base reaction, where the electron donor is the base and the electron acceptor is the acid. So I like to think of it as a base is a very special type of nucleophile and acid is a special type of electrophile. But if you are in acid-base land, you want to use those terms rather than nucleophile electrophile because it's more specific. So I've tried to put it all in like a summary diagram that kind of puts it together. So in a reaction, electrons are going to flow from a HOMO, which is a donor, on the nucleophile molecule, which could be a base, depending on the type of reaction. It's going to the LUMO acceptor MO that is on the electrophile, which could be an acid, depending on the type of reaction it is. So that's kind of like pictorial representation. Questions on terms here before we put into practice? Yeah.
So every base is a nucleophile, but not every nucleophile is a base, right?
Yeah. Mm-hmm. That's exactly how I like to think about it. Yeah. So if we look at this practice over here, I'm going to do the first one with you, and then I'm going to have you try the other two. So the first question to ask when we are given a scenario like this where we have all the atoms, but we need to supply curved arrows, is first, are we in acid-base land, or are we in nucleophile electrophile land? And to determine that, we have to look, is the only thing that got transferred between the two molecules a hydrogen? So for this first scenario, is the only thing transferred to hydrogen? Yeah, she had a third hydrogen over here, and now she is over here. So we are in acid-base land. Okay. So then we need to think about which one is the electron donor and the electron acceptor. So between the left and the right, we have different charges, negative and positive charge. Which do you think is going to be the better electron donor? The negative, right? So this is going to be our donor species. And what do we call the electron donor in an acid-base reaction? The base. And that's our Lewis definition of base. We also have Bronsted-Lowry that talks about the hydrogens of, like, base is a hydrogen acceptor. But in organic chemistry, we care a lot more about electrons. So we would say that this is a Lewis base. It's also a Bronsted-Lowry base, but. And then our acid would be over here. So, what's a good donor orbital on this molecule? Yeah, we have a lone pair. And we have lone pairs on the sulfur and the nitrogen. But this nitrogen is where we have the negative charge, so that's going to be our best donor. So, lone pair on nitrogen. And then, let's scan this for good accepting orbitals. So, do we have an empty 2p orbital? No. We're only going to have empty 2p orbitals when we have incomplete octets. And this molecule, everything has a complete everything. Oxygen has a complete octet. Okay, do we have any pi star molecular orbitals? Well, do we have any pi bonds? No, so we can't have pi stars. Third one, we're looking for sigma star orbitals. And here, that's the only option we really have, right? So we have sigma OHs. So I guess our only accepting orbital is a sigma star OH. Okay, so our lone pair is going to go from the lone pair on the nitrogen to the sigma star OH. And here we're putting electrons into an antibond. So what happens? Thank you. So we need to put these electrons that were in the bond onto the oxygen. We broke the bond by putting electrons in the antibond. Amazing. And hey, if we check this out, this arrow, its consequence in the product was, I'll actually like draw this out over here. So imagine we had OH and OH. Like this turned into, oh wait, I'm so sorry. The yellow arrow turned into that bond. It created that bond between the nitrogen and hydrogen. And then, initially, this oxygen had one lone pair on it, but now it has two. And so, the second arrow turned into that lone pair. So, take a minute or two and try these other two examples. And this is on page 38 of the problem set. 38, yes. Is your name Rima? Rima. So for this middle example, are we in acid base land or are we in nucleophile electrophile land? We're in nucleophile electrophile land because we're only in acid base land if only a hydrogen is transferred between the two molecules. And here we see this whole OH2 has been added. So we're in nucleophile electrophile land. So which of these two things, the left or the right, seems like it wants to accept electrons? Which wants electrons? The left, it has a positive charge, so that's going to be our electrophile, and this is going to be our nucleophile. Okay, what's our good acceptor on our electrophile? Yeah, the 2p orbital on the carbon, so that's going to be our acceptor. And what's our good donor on our nucleophile here? Yeah, the lone pair is going to be our best donor. So the lone pair in the oxygen is going to attack the positive charge, the 2p orbital on the electrophile. And then, do we need to break any bonds? No, we didn't put electrons in an antibond, so we're done. Okay, last one. This one's a little bit tricky. Are we in acid base land or are we in nucleophile electrophile land? Acid base. Because the only thing that transferred between them was a hydrogen. And so, based on these two molecules, is the left or the right the base? The right one is. We know that she's hydroxide. And we also know the electron donor is a base for our terms. Okay, what's our good donor orbital on our base? Lone pair. Trend alert. Lone pairs, good donors. Okay. Well, we know that this lone pair on the oxygen, based on what we see over here, we know it has to grab the hydrogen. So we know that we are going to do this arrow. But then, if we broke this sigma CH bond, what orbital do we have to put electrons into? The antibonding orbital. So we know that this had to have attacked the sigma star CH because we know we've broken that bond, and we know we've broken that bond because she is not there in the product. Okay, but now, normally you would just break it and put it on this carbon, but we see that there's some other stuff that happened here. So let's think about what other bonds we need to make and break. Well, we need to break the pi bond here, make it a single bond, and we need to make a pi bond here. So if we are breaking a pi bond, where do we have to have put the electrons? An anti-bonding orbital. So we broke the pi CO, so we're putting electrons in the pi star CO. And where's our source of electrons? Well, it's this sigma bond that we are breaking, right? So we need somewhere to put the electrons, so the electrons are going to go from that bond into creating this double bond, and that, putting the electrons in the pi star CO, is going to break the pi bond. So we would say our donor for this second interaction is the sigma CH going into the pi star CO. And that gives us these products over here. So this arrow corresponds with this interaction, and these arrows correspond with this interaction. Yeah.
Isn't the sigma CH going to the like that CC bond?
So it's going to become a pi CC bond, and we draw our arrow to this because that's where the electrons are going, but we are really putting it into the antibonding orbital, which makes this molecule break that bond, the pi bond, and then it creates the pi CC bond at the same time. So it's kind of weird, like what it's at and then what it's becoming versus what it ends up. But we do it based on the orbitals that are on the molecule currently. Yeah. Cool. Yeah, Masha.
So I think that when we study, so is this arrow the yellow one going to the C, right? It's not going to the bond, right?
So this one is going from a bond to another bond.
But because when we look at arrow pushing and all of that, like
For resonance?
in general for like gen chem, is it like that the arrow pushing can go like from a bond like to an atom, that it needs to go to an atom?
You're thinking about resonance rules. So resonance rules, I liken it to, it's like bowling with the gutter things, shields, where there are a lot more rigid rules for resonance arrow pushing. Resonance arrow pushing, you can never break a single bond. But when we go into actual reactions of molecules interacting with each other, we can do far more things.
So this bond is not going to the C. It's going to, because we said, so it's going like the arrow going from the bond to a bond.
The electrons that were in this bond have wound up in this bond now. Yeah. It takes a little practice, but I do need to keep moving. I'm welcome to answer questions afterwards. So let's do this practice together. So you did this molecule A MO diagram, and I've given you the MO diagram for B. And now what I want us to do is predict how these two molecules are going to interact together and draw what the product is. So in order to do that, what we need to do is we need to identify the HOMO and LUMO on each MO diagram. And when we have an MO diagram, it truly, like, we don't have to think about it. The HOMO is just the highest occupied one. So our HOMO over here is our lone pair on nitrogen. Our LUMO is the lowest unoccupied, so sigma star NO. So let me write these out. The HOMO of A is lone pair on nitrogen, sigma star NO. Okay. And then in molecule B over here, what's our HOMO? Yeah, the lone pair on chlorine. In our LUMO, there we go, pi star CO. So now that we've written both of them out, what we're going to do is we're going to look at the molecules and try to figure out which of them is going to be the better nucleophile and which is going to be the better electrophile. So let's start off with the donors, like the HOMOs. Which one is a better donor? Lone pair on nitrogen or lone pair on chlorine? Nitrogen, because we said chlorine was not good donors. So I'm going to say the best donor is on molecule A. And I'm going to kind of say the worst donor is on B. Then let's talk about accepting orbitals. Which one's going to be a better acceptor orbital, the sigma star or the pi star? The pi star, because pi stars are lower in energy than sigma stars, so they're going to be better acceptors. So our winning acceptor orbital is on molecule B, and molecule A has the worst acceptor. So based on that, between molecules A and B, which do you think is going to function as the nucleophile for the reaction, like the biggest donor for the reaction? Molecule A. So our nucleophile is going to be this molecule, and then our electrophile is going to be the one with the better acceptor between the two. So the interaction we have is a lone pair on nitrogen is going to go into the pi star CO. So let's draw our lone pair on nitrogen. And then we're attacking the CO, and we attack the carbon side because it's more partial positive, because it has the bigger lobes of the antibonding orbital. And then we push up, because if we put electrons in antibonds, we break the bond. So we draw out what the product is, and for this, I literally like to just draw everything I didn't change. So I know all these single bonds are still here. I know I created a new bond to the nitrogen. And then that nitrogen still has two H's and an OH on it. And then I trace what changes my arrows made. So this yellow one created that bond. And then this blue arrow added another lone pair up to the top. So that's negative. And then lastly, our nitrogen is going to have a positive formal charge because it has 4 bonds now. So, this is the like exam type question that you're going to have, where we will give you a molecule, we'll make you do a full MO diagram, identify the HOMO LUMO, then we'll give you another molecule and say predict how the first one that you did an MO diagram with reacts with the second one. That's going to be like 1 of 9 pages on the exam. Questions about this?
Can you just explain why we did that, the non-bonding N over the non-bonding CO?
Yeah, so we say that good donors have lone pairs, yes, except for on halides. So halides are not great donors, even though they have lone pairs. Other questions on this? Okay. Ready for our second big transition of the day?
Yeah.
Oh. So let's talk about acidity. So, in Gen Chem, when you did acidity, you were doing a lot of equilibrium stuff, right? You were doing like KEQ, where you have like products over reactants, and you were talking about Ka a lot. And then pKa was just kind of like a bonus thing that you did some math on, of like do the negative log of that. We want you to have strong associations with pKa because this is what is used as a measure of acidity for all of like organic and biochem. So lower pKa is stronger acid. But what do we mean when we say a strong acid or a weak acid or base? So strong here just means it's very reactive, whereas like, for example, a weak conjugate base, it's weak because it's very stable. And so oftentimes we're using strong and weak as a proxy for stability or reactivity. Now, one of the things that I write down on pretty much every acid or base question is a strong acid has a weak conjugate base. I abbreviate it with SA equals WCB. The flip of it, strong bases have weak conjugate acids, is also true. But this is kind of the guiding light for me because acid-base typically requires us doing some mental gymnastics to like get things into terms that we can compare them. So let's do our like little face-off YouTuber boxing match event of the century where we are going to compare two things and we're going to say which one is more acidic. And the strategy for doing this is we are going to draw out the conjugate bases of each of them. So let's start off with this first example. The conjugate base, we're just going to remove a hydrogen, so NH2 here. And then this one's just going to be NH. And what else do I need on this nitrogen if I've removed a bond? We need an extra lone pair. So what else? A negative charge, yes. Because we could just put a negative charge and not write the lone pairs. Because for skeletal structures, lone pairs can be implied. So again, it's that visual skill of like a nitrogen with only 2 bonds, she's going to be negative. Nitrogen with 4 bonds, positive. Okay, so now, which one, left or right, is more stable? The left. She's neutral, whereas this is basic. So this is more stable. So it's our weaker conjugate base, which means the NH3 plus is our stronger conjugate acid. And actually I'll do that in green because winner in green. Okay, let's do the same thing over here. So we have our NH minus and we have an O minus. Which one's more stable, nitrogen or oxygen with a negative charge? Oxygen, why? More electronegative. So this one's more stable. So it's our weaker conjugate base, meaning OH is the stronger acid. Strong acid, weak conjugate base. See the mental gymnastics, it's a little bit much. Then, okay, we're going to compare O minus and S minus. Now, if we use the same criterion we just used, electronegativity, we would say the O is more stable. But we actually have a competing effect here. So a competing effect with electronegativity is atomic radius. So the metaphor I like to use is like imagine you have a negative charge and you're holding it in this like little mini beach ball and compare it to the same amount of charge in a big beach ball. The negative charge is going to be more stable when we can spread it out more, right? And so that's the difference in atomic radius between oxygen and sulfur. Sulfur is much bigger, so if it has a negative charge, it can spread it out a lot better. And so it's going to be the more stable, or our weaker conjugate base. So this is the stronger acid. And the general rule is if you're comparing things in the same row of the periodic table, so like here CNOF, then you use electronegativity, and I'll tell you. So oxygen's more electronegative than nitrogen, oxygen's the more acidic. If you're doing in the same column, S and then selenium, I think is next. In the column, it's based on atomic radius. So the bigger atomic radius, sulfur is going to win. And also, if we look at pKs, like this one's going to be around 17, and this one's going to be around 8. So you can see it's a pretty significant difference. Okay. Then, conjugate base of these. O minus. O minus. Which do you think is more stable? Left or right? Left. Why? Resonance. So, and actually, real quick, what's the hybridization of this oxygen? It appears to be sp3. It has a lone pair as next to a pi bond, so it's sp2, our neighbor rule. So, yes, we have resonance in here. And what that means is we can spread out that negative charge among all three of these atoms. So a spread out delocalized negative charge versus a localized one, it's just stuck on the oxygen here, it's definitely going to be more stable with our resonance. So our weaker conjugate base is over here. So this is our stronger acid. Then we have the kind of younger sibling of resonance, which is called induction. So the way I typically think about induction happens when we have electronegative elements, typically halides, on a molecule. And, you know, resonance is like, hey, I'm your ride or die. I'm going to take on this negative charge with you. We're going to spread this out, do it together. Induction is like, I'll tug on the electrons a little bit, but I'm not going to fully take on the charge. And so that little tugging that these fluorines do, kind of dipole moment things, it is still helping to spread out the negative charge a little bit. So because of that, this is more stable because of that inductive effect, spreading out that negative charge. So this is our weaker conjugate base, meaning this one's more acidic. And then finally, when we have no other effects to check, what we check is for hybridization. So if we have a negative charge on a sp2 carbon versus an sp carbon, the winner, the one that's going to be more stable, is the one that has more S character. So let's say you imagine you have an sp2 orbital. That is 1 parts S, so 33% S, and 2 parts P, 67% P. What percent S is an sp orbital? 50. So which one has more S character? sp. So we say things with more S character can better stabilize a negative charge. And the way I like to think about it is, think about the sphere shape of an s orbital. It holds the negative charges closer to the positively charged nucleus, so there's like a favorable electrostatic interaction, whereas a p orbital holds it a little bit further away. So it's better able to stabilize that negative charge by holding it close to the nucleus. So this is our weaker or more stable conjugate base. This one's more acidic. Now, these rules, the like Hario rules here, they are useful when you're only comparing one difference. If you're comparing like differences across electronegativity and atomic radius, we don't have an easy set of rules for that. And so that is indeed why we are making you memorize these. So the thing I did to try to make it a little bit nicer for you is I tried to do like a little yassified kind of chart and some like color gradation and just make it look nice, because we are going to ask you to fully like have this memorized. And again, it's because we need you all to have a frame of reference. If I said the pKa of HCl is like -7, I need you to be like, oh shit, that's way more acidic than H3O plus. Like it needs to have some sort of significance. Or if I say later on that like an alpha hydrogen between a dicarbonyl has a pK of about 13, like you need to be able to place that in your mind of like, oh, okay, so it's between an ammonia and like an alcohol. Which also I think I have one type on this, which is this should be ammonium for NH4 plus, and ammonia is NH3. But there we go. So commit it to memory soon. Any questions on the face-off so far? Yeah, I'm sorry about the memorization. I had to do it too. Okay, so there's a connection between pKa and KEQ, our equilibrium constant. So just brief recap of Gen Chem. If our KEQ is greater than 1, do we favor the products or the reactants? Products. So we're going to favor the product direction. If our KEQ is less than 1, we favor the reactants. And then if our KEQ is equal to 1, it's about even. So if we have an acid-base reaction what we're going to do is we're going to identify the acid on either side of the equation. So which molecule here is the acid, the left or the right? The left. Okay. And what functional group is this? There it is. Acid's in the name. Okay, so what's the pKa of a carboxylic acid? And you can scroll up if you need to. 5. Okay, so that's the acid over here. And then if this was the base, then we know this is its conjugate acid. So ammonia NH4+, what's its pKa? 9. Okay, great. So these are our pKa's. So for an acid-base reaction, if we have the pKa's of the acid on either side, then we can do 10 to the power of the pKa of the product acid minus the pKa of the reactant acid. So that's 10 to the 9 minus 5. So our KEQ is going to be 10 to the 4. So is this reaction going to be product favored or reactant favored? Product favored. It's bigger than 1. Cool. So that is the skill that we want you to be able to do. You'll see it on the problem set. I'm probably going to skip practice 4, which is a challenge problem ranking. Actually, we can do B together. So we're trying to rank the acidity here. So my first question for you is, what do you think is going to be the least acidic? C. I have 1 vote for C. Are you, yeah. Maybe let's start off by IDing functional groups. What functional group is this? What functional group is this? What functional group is this? Aldehyde. So we have carboxylic acid, aldehyde. Carboxylic acid, the hydrogen is acidic. It's about 5. So we know that these two are going to be pretty darn acidic. Aldehyde hydrogens are not acidic. Like their pK is like greater than 20. So we know our worst acid here is going to be A. Okay, so now between B and C, what's the difference between them? Yeah, we have fluorines over here, so we have inductive effect. So that's going to make this a better acid. So C is the best, and then B is in the middle. Y is induction. I guess we can do the A example too. So like here, these are sp3, this is sp2, and then this is sp. I'll draw the hydrogen. So which one's more acidic? Well, the one with more S character. So C's most, then B, then A, and Y, it's because of S character. Cool. So that's kind of acid ranking. So now, we are going to look at one of those extra challenge problems that we do on Fridays here, which are exam level or PSAT level questions. And this is in the section notes packet if you're using that. If you have printed problem sets, it's in the back of the problem set book, the orange book. But I'm going to be giving you a few minutes to try approaching this on your own, but I'm going to talk about a little bit of the setup to get you started. So, this molecule is a common dye used as a pH indicator. At low pH, the molecule is colorless and has the structure depicted in A. Okay. Deprotonation of A with hydroxide yields water and a monoanion B. So we know that this thing is negative charged, and we know that OH minus is going to deprotonate the other molecule, right? What are the only hydrogens that look like we could deprotonate them? Literally the only hydrogens on the thing, yeah. So we know we're definitely going to have like that arrow as part of our answer. We're going to deprotonate it. But then let's keep reading. It's going to deprotonate, yield molecule B, which appears pink, and in which there is no longer an sp3 hybridized carbon. So where is our sp3 hybridized carbon in molecule A? Right in the center. So somehow, from this, all in one step, we're going to draw more arrows, and we have to make sure this no longer is sp3 hybridized. So we have to break some bond here. right? Because we can't add another bond directly to it without breaking something. It already has a full octet. So that's what I want you to kind of think about and try to figure out what you can do with your arrows. Then part B you can do even if you don't solve part A. It's going to ask about KEQ related to pKa stuff. And then part C is going to say, hey, we have this other molecule that looks really similar to molecule A, but we've added some bromines. What do you predict the pKa of this to be if we give you that the pKa of this is 9.5? So I want you to take like 3 or 4 minutes. Try to think through some of this. Is it Rima? So what do you think about it? What do you think is going on? Yeah, it would stabilize that conjugate base, right? So you this would be something less clear. And again, as a base, you always have to be multitasking going back and forth. How do you do with the arrows? In part A? That's the hardest part to do. What curve arrows could you do? What's going to be for the best if you had to? So maybe start thinking about if we ground out hydrogen, we have to do something with the electrons in that OH bond, right? So try putting that somewhere else and see where that goes. I know that without the printed, or actually, you have a printed copy of this. It's in the orange book. It's like P sets here, and then the extra charm bonds are all the way at the end. So like in the last however many. Yeah, totally. Okay, so let's try to regroup with part A here. So we know our OH is going to deprotonate the hydrogen, and we are going to have to do something with these electrons, right? And I think our instinct, generally speaking, is we would just put it on the oxygen. But then that's not going to break this bond. So we need to do something else with these electrons. So does anyone have a suggestion for where we should draw our arrow to? Yeah. yeah. So we are gonna draw the arrow, and we're gonna draw it to this bond here. But what we're saying with it is the electrons that were here are going to make a double bond here. Cool. But then this carbon already has 4 bonds, so we need to break a bond. So the easiest bond to break is going to be the pi bond. Let's move that pi bond down. Okay, and then let's move this pi bond down. Let's keep the chain going. And then once we're on the sp3 hybridized carbon, now we don't have a pi bond to break. So we have to break one of the sigma bonds. And the easiest one to break is our sigma star CO, or like the sigma CO bond. And it's because if we have the sigma CO and the sigma CC, sigma star CC is our antibonding orbital, which of these is lower in energy? CO. So that's going to be the easier one to break. So for drawing the product that we get out of this, it's a bit of a beast to draw, but we are going to keep the same all the molecules that we didn't react with. So blum, blum, blum. And then we're going to make sure that we do the changes reflected by our arrows. So we made a double bond with this oxygen from this arrow right here. And then we kept this double bond the same, but this is the new double bond that we made. We put a double bond on the outside here. And then we had our oxygen that we kicked off. And then we still have all of this ring. So right now this drawing component is going to feel pretty challenging because y'all have not gotten used to drawing big molecules yet. It will get faster. It's just something that comes with practice. Cool. So we have our molecule B. And can you confirm we don't have an sp3 hybridized carbon? Amazing. Okay, so now KEQ question. They tell us that the pK of A is 9.5. And then we know the pK of water is about what? About 16. So we use 10 to the power of the pK of the product, 16, minus the pK of the reactant, 9.5. That's going to be 10 to the 6.5. So does it favor the products or the reactants? It favors the products, yeah. And that there's a point there, but it kind of blended in. Then part C here, comparing this structure to this structure. This structure has these bromines, so what effect is it feeling? Induction. And we know induction makes things more acidic because it stabilizes the conjugate base. So we would expect this to be more acidic than A. A was 9.5, so of our options, we're going to go with pK of 7. Cool. And then I'll leave you with D to think about on your own, but it's going to be asking, okay, it's presenting a bunch of bases. Which of these bases are strong enough to where they would deprotonate this guy, but they would not deprotonate this guy? So you want it to be a strong enough base to deprotonate this, yes, but not deprotonate this. Because if you think about this being more acidic, if this OH can deprotonate this original molecule, the OH can certainly deprotonate something that is more acidic, right? Like if it can already deprotonate something at 9.5, it can deprotonate something at 7. So that is one thing to think about. And then there's another extra challenge problem if you want to look at for some extra practice, but I would prioritize the problem set. Cool. Well, thank you for coming to section. That's all I have for you. I'll stick around for some questions. Have a good weekend, and we hope to see you on Monday with Help Room.
Cool. So the only thing you have to memorize